Hello. It's the 24th of July, 2015, and this is episode 16 of the Unseen Podcast. Tonight, we are happy to welcome our special guest, Dr. Brian Koberlein. Hello, Brian.
Hi, thank you for having me.
Brian, tell us a little about yourself.
Well, I'm an astrophysicist at Rochester Institute of Technology, and I'm also a science communicator, and I have a regular blog that I write on called One Universe at a Time, and you can see me all over the net on various places.
Yeah, now, one thing that we should point out, you have a podcast also called One Universe at a Time.
Also called One Universe at a Time, yeah.
And it's a rather unique format. It begins with you interviewing a researcher about his or her research, and then they turn it around and ask you questions about astrophysics, which is pretty cool.
Right. Everybody gets to ask questions and everybody gets to answer them.
Yeah. Now, tonight on our panel, we have, let's start with Patrick Festa. Say hello, Patrick.
Hello, everybody. It's just little old me, Pat Man. I'm just basically a science enthusiast. And by the way, Dr. Koberlein, it's a pleasure to meet you. I have watched your weekly space hangout with Tony Darnell, I think it is. And it's actually a great pleasure for me to finally actually talk to you face to face, so to speak. And my self-inflicted job is to try to promote the science and critical thinking throughout the social networks.
Okay. And we also have with us Adam Synergy Smith.
Hi. Glad to be with you again. It's a pleasure.
Now, I should point out that Adam is in the UK where it's about 2 o'clock in the morning. So hang in there, Adam. Thanks for joining us at this ridiculous hour. And we also have with us Chiro Villa.
Hey, how are you, Paul, and everybody?
Great.
It's not 2 o'clock in the morning for me. It's only 9. But it feels like 2 o'clock sometimes. No, so I'm very happy to participate in this broadcast as well. I've had some communications with Professor Koberlein myself, but never had the chance to be able to speak to him in person. So very happy to be here.
I gotta be honest. We have very modest objectives, which is to make Brian a science communication superstar, totally eclipsing Neil deGrasse Tyson and all those other folks.
Actually, I'm here on his advice. He advised me, well, not me personally, but he gave some good advice once in an interview that I watched, Neil deGrasse Tyson. He said there are only a few thousand astrophysicists on the planet amongst the population of, 6 billion people. So he said, if you get the chance to talk to an astrophysicist, take it. So I'm here. One of the best things he's ever said.
And, Adam, I think maybe we should start off with your questions, sort of to get people to get to know Brian a little better.
Okay. Yeah, fine.
Yes.
Hi, Brian.
Hi.
Let's go back to the beginning, first of all. When did the young Brian Koberlein first realize that he wasn't going to follow in the steps of his father and his ancestors and farm the Midwest of America? When did that first sort of dawn on you?
Well, when is the time that I knew? Oh, when was I hoping for it? Growing up on a farm, I always had an opportunity to see dark skies. And so, as long as the sky was clear, I could go out just literally right out in my backyard and see the Milky Way. I could see, the constellations, the Andromeda Galaxy. So I had all of that opportunity to see the stars from being very young. I don't know that I thought of astronomy or astrophysics as being something you could do for a living until I was much older. So I was very interested in science, but and I was obsessed with astronomy since about the age of 12. So when I was 12, I got two things happened. One is I got a book called Our Universe. It was put out by National Geographic. That was just this gorgeous full color book with all this information and images. And that had come, I got that on Christmas while Cosmos was still airing.
Oh.
So those two combined, basically lit a fire under me, and I was obsessed ever since.
That's cool. Okay. So you went to university?
Yeah, I went to university. It was actually quite fortunate to be able to go to college. And then I guess probably around my junior year, I was devoted to getting a physics degree, and that's about the time that I started thinking about going to graduate school. And so then, after graduating with an undergraduate degree, I went to graduate school at Connecticut, University of Connecticut, and then got my PhD, and I've been in the field ever since.
What do you most enjoy about your job? Is it teaching, or is it looking at the universe, or is it a combination of both?
I think it's a combination of both. I think, I enjoy learning new things about the universe, particularly when there are things that are unexpected, things that we don't expect to find, and then we turn out that that's the way the universe works. But I also enjoy telling people about it. I think it's important that, we understand science in general, and truly for astronomy, it's a human endeavor. It's what humans have done for centuries, if not millennia. And the other thing that we've done is storytelling. And I think communicating the stories of the stars and communicating what we find to others is the second half of that piece.
Did you ever get a sense of that you were entering into so-called golden age of astronomy?
I don't know that I ever had a
excellent.
sense. The timing is excellent. Yeah. I mean, when I was an undergraduate, one of my professors said, we have 5 models of cosmology. We have 5 models of the universe, and any of them could be right. And by the time I got my PhD and had gone on into universities to teach, we now know that all of them are wrong. But we now, cosmology has changed from kind of a theoretical field to an actual applied field. And that's a radical change for what we've been at.
Right. Was that mostly enabled by the microwave background measurements?
It was a combination of the microwave background measurements and the Hubble telescope. And more recently, ground-based telescopes with adaptive optics and things like that. But the Hubble telescope really opened up the field of cosmology because it could allow us to see really deep field areas that we couldn't see before, and large redshifts that we couldn't see before, and to do that with a high resolution. So it was really that when you had the confirmation of dark matter, when you had the discovery of dark energy, that kind of transformed the way we view the universe.
I'm sorry, Adam, I interrupted you.
No, it's quite all right. I forgot what I was going to say.
Well, we wanted to ask Brian a little bit about his trip to Chile recently, just the last few weeks.
Yeah. It was an amazing experience.
You visited the ALMA, or did you go other places?
We were at ALMA and Gemini and CTIO, which are very close to each other. So we got to see, both optical and radio telescopes, and also see, kind of the long-term plans of where astronomy is going in Chile, which is going to be huge. By 2020, I think 70% of all astronomical infrastructure are going to be in Chile.
Wow. Now, the ALMA is kind of a new beast, isn't it? I mean, it's millimeter wave.
It's relatively new, yeah. In fact, it just went fully active when it was in a construction stage, and now it's kind of transforming from the construction stage to the actual full observing stage.
Because we're seeing images from that look almost impossible.
Yeah, they're incredibly surprising what they can get.
Now that's not an optical telescope. I should point out that's like somewhere between radio and infrared. It's millimeter wave. right?
Yes, it's millimeter and submillimeter. When you get to submillimeter, you're almost in the far infrared. So it is, it's an antenna array, and it gets millimeter radio microwave images that are roughly at the resolution of Hubble. So it's kind of, the radio telescope that can resolve things at the resolution of Hubble, which is really kind of amazing.
Yes. They resolved a planetary disk much better than I thought they could have. But
yes, and that's the thing that makes ALMA so powerful, is that those frequency ranges are kind of tuned for looking at cold molecular gas. So the cold gases that are around the universe emit light in the same way that other things do, but it's in the microwave and the millimeter range of wavelengths. And so to be able to image them at the same resolution that you would image, something with the Hubble telescope is a new field of astronomy almost. We've never been able to do that. And over the next 10 to 20 years, it's going to be an amazing ride.
Right. Adam, do you have any other questions?
That was, I think you were talking then about HL Tauri, the baby planetary system, baby solar system that was imaged last year by ALMA. That was amazing, absolutely amazing. That you can see the gap in the protoplanetary disk actually, being formed. Planet,
and what's amazing about that is they're just getting started.
Yeah, that was the first one, so you would presume they're only going to get better at it.
Yep.
Yeah. One thing I did want to ask you, Brian, how do you manage to keep up with the incredible, phenomenal number of academic papers that are published every day? How do you manage to keep up to date?
I'll be honest, I don't. Nobody does. Nobody does.
Yeah.
You kind of, that's part of the reason that doing the blogging and stuff actually helps, is that it forces me on a regular basis to actually see what's out there. And so you kind of get a cursory idea of what's out there to begin with, and then you go deeper in the areas that you're actually researching in. But nobody keeps up with all of it.
Like me, you just read the abstract.
That's right. There are times when you're lucky to get through the abstracts.
Yeah. Okay. You obviously see public outreach and science education as being really important, because it's something that you do consistently, pretty much every day. You write a blog post.
I try, yeah.
Why?
Well, I think there's a lot of value in doing science, but there's traditionally been this kind of split between the people that do science and the people who talk about science. And, if I do a research paper and it gets published, if it's doing well, it may be read by a dozen or 24 people in the field, maybe. So if I have an audience of 10 in an academic circle, that's huge. But at the same time, we don't do science in a vacuum. In most countries, the scientific endeavors are funded largely through tax dollars. They're government initiatives. There are some private initiatives, but the bulk of heavy lifting in science is done through tax dollars. So basically everyone's paying for it. And they should have something back in return. It shouldn't just go into a hole and help people like me, and then, I go off and do my thing and 10 people read it. If we're going to be serious about science, we also have to be serious about communicating science. And that goes beyond our area of specialty. I think you have to communicate this to the general public. and I think it's a way of giving something back.
Yeah, sure.
But I also think that it's important for people to have an understanding of where science is. And in my area, it's astrophysics, but just in general, people should have an idea of what are the questions that are being explored and why are they exploring them. And, it doesn't just come into the fact that we're spending our tax money on this, but also our future as a species is dependent somewhat on the choices we make involving science. And so we can talk about issues of global warming, or we can talk about issues of asteroid mining, but they will both have an impact on human society. And how we approach them and what we do as a collective whole matters.
You are very good at describing quite complex astrophysical phenomena to people that don't necessarily know exactly what you're talking about.
I teach freshman physics. I've seen things, man.
Is that a skill that you've developed over the years?
I think it comes in twofold for me. One is I do teach a lot of introductory courses. The department where I work, has an emphasis on, we have a lot of engineers that have to get trained. And so they have to take physics, and they don't like physics, and they take astronomy because it's a fluff course, they think, to get a science cred out of the way. So I'm used to teaching people that are not necessarily interested or motivated to learn the high level stuff. But I think another part of it is that I'm the first person in my family to go to college, and so
you and me both.
You and me both.
Yeah.
And so a lot of my family have been, somewhat interested in what I do, and I have to be able to communicate that on a level that they can understand, because they're intelligent people, but they haven't had formal training in physics or astrophysics or astronomy or anything like that. And so I think it matters, having that practice of being able to talk to my parents or, cousins or people who grew up with me, I think is part of that experience, is you learn how to simplify it down to the core areas.
Okay.
Wow.
How do you... Go on, Paul.
I was just going to second Chiro's, not Chiro, I'm sorry, Adam's assertion that you're very good at clarifying these things. And you don't leave out the controversies, which is good. Not all scientists agree on something. That we need to know that.
Right.
If there is a firm scientific consensus and a factual basis to things, we need to know that too. And you recently blogged, for example, about the standard candle, and how we know that dark energy is real. And,
right.
And there is pretty much a consensus dark energy is real, although there's some questions about how standard the candle is, but there's other evidence, right? So that was, to me, was very helpful, because I can't follow all that literature, so I'm glad that you do, and so that kind of thing is it's important to know when to the public. Okay, scientists agree on this; they don't agree on that, and here's why. And we'll get into more of that a little bit later, I think. But
well, I think that's part of it too. Is that when I'm doing my blogging and other outreach things, I think one of the things that you can kind of fall into a trap of as a scientist is that people are idiots, and it stems from the idea that so many things that you've learned for so long, most people aren't familiar with. So it's very easy to go, well, everybody should know this. Well, no, not everybody knows this. Not everybody knows about conservation of energy or standard candles or anything like that. And I always try and keep in my mind, people are not stupid. People are very intelligent. They may not have the right education, or they may not be interested in what I'm interested in. But I think you can communicate both the accuracy and the debate within science if you focus on what the evidence actually says. The evidence may not be clear. The evidence may be missing, or the evidence may be definitive, and I think people can understand the basic ideas of what's going on in terms of astronomy or anything in science if you give them half a chance.
Great. We had Ben Tippett on at our very first episode, and he took pretty much the same attitude, that anybody can understand it if you explain it right.
Right. I try and take the idea that you can understand it, but to prove it to you, you're going to have to go and get a PhD.
Right.
I can't prove it to you.
Right. Adam, you were going to ask him, I think, who is the scientist he most admires?
I was actually going to ask him about if he gets any mail from so-called Crank. You must do.
Almost.
Do you?
I get email almost weekly, and
you've made it, Brian. You get mail from Crank.
Well, at least I've made it to the Google searches. They can say, "Well, Tyson's ignoring me. Maybe I'll go after this guy."
Yeah. So, who are your heroes? We've all got heroes of one kind or another. I admire people like yourself, scientists. You've helped me a lot. You have. You've helped my understanding. Seriously, you have. I would list you in my top 4 people that have helped me personally understand the universe. Along with Pamela Gay, Fraser Kane, and Emily Lakdawalla. So, I mean, sorry you're 4. But
it was in no particular order.
That's not a bad circle to run in.
No. Well, Emily's wonderful. If you want to know about planetary science, you follow Emily. Yeah.
Yep.
So who do you admire, Brian?
It's kind of hard, I mean, I can go through historical scientists, and I had a lot of a lot of respect for Feynman in terms of how he approached problems. Richard Feynman, and I think when I was in graduate school, I think he was probably my big hero. Probably because his lectures on physics really saved my butt in grad school. So, I
really don't know why there are any physics textbooks left when you've got the Feynman lectures, but
there are parts of it that are outdated.
Yeah.
So it could be updated, but I think there's, one of the ones that's I think more unusual is Emmy Noether.
Yes.
She was a mathematician and theoretical physicist, and she's kind of the unsung hero of science, and certainly the unsung hero of physics, in the sense that what she did and the theory that she came up with, which is Noether's theorem, revolutionized science. I mean, it revolutionized physics. You can actually look before her and then after her, and you can make a clean line of demarcation in terms of how we did physics. It was that revolutionary. But because it wasn't a new specific theory, it influenced everything. And because she was a woman, she didn't get the notoriety that other people did. So Einstein, for example, considered her to be more intelligent, and that her work was in many ways more important. And it does. It influences everything from the way we do Newtonian physics to general relativity to particle physics. It's all there. She's in every single field because of that theory, and nobody knows about her.
Could you repeat the name of the person, Brian?
Yeah, I was just about to say that. And the name of the theorem?
It's Emmy Noether, Noether. Maybe Noether. It was German, so
Noether, I think, something like that.
Noether, yeah. I don't even want to try and pronounce these names, but it's her theorem. It's named after her. It's Noether's theorem or Noether's theorem, or
and the 30,000-foot view of it is, if I understand it, is that if there's a conserved quantity, there's also a symmetry that corresponds to it.
Yes, that's the basic idea. So you can say anything that is unchanging in time has conservation of energy. So if something has conserved energy, a mass on a spring, for example, if it were never losing energy, would keep doing that forever. And that symmetry in time means that there would be conservation of energy. If you were in completely empty space and tossed a ball, and it would keep going in a straight line at the same speed forever, that symmetry of translation in space means that momentum is conserved. And what makes it powerful from a theoretical standpoint is that symmetries are easy to model in models. You can find some conserved quantity. You can find some what we call an invariant quantity, and then you can connect that to a conserved quantity, and you're done. So, when I do computational physics, for example, one of the challenges is to make sure that your computations don't drift over time, because you're always going to have a little bit of error in your computation. So if you take that little bit of error and you plug it back in, you're off a little bit. And if you do that again, you're off a little bit. And so you can just kind of worm along to a wrong answer.
Propagating a lot.
Yeah, you're propagating your errors. But one of the tricks you can do is you can say, what are your conserved quantities? If energy is conserved, you lock it. If momentum is conserved, you lock it. And so every time you run an iteration, you run the iteration and then you adjust it back so that momentum and energy are conserved. Then you run it again and you adjust it back. And every single time you're just ranking it back so that now you don't have that drift. And without that type of symmetry, you couldn't do that. So computational physics would be much more difficult without that theorem.
Yeah, it's a beautiful idea. And
it's one of the most beautiful ideas in science, I think.
Yeah. And, okay. Adam, any other questions?
You wrote a book, Brian. Can you tell us about your book?
Yeah, Astrophysics Through Computation. I would say I wrote half the book because I did have a co-author. It's a upper level undergraduate textbook on computational astrophysics, and it's the type of thing that you can do on a laptop, which is, again, something that's radically changed in my lifetime, in the sense that
I read recently that most astronomers have to write code. Vast majority of both observational and theoretical astrophysicists write their own code.
Yeah, and most astronomers, and people imagine astronomers and astrophysicists as, maybe astronomers are the people who sit behind the lens of this really huge telescope, and, astrophysicists have this big, huge white chalkboard full of equations, and what we all do is we sit in front of a big screen computer and hack away all day.
Some of them may enjoy doing that. Some of them surely must bemoan the fact that they spend most of their time sat behind a computer. Surely some of them would rather be, many of them, observational astronomers, would rather be looking at the stars.
I know from some astronomers, when you're running your observations, particularly if you're doing them at night, it's cold outside and it's, not comfortable to be out there, and you're in a warm room sitting in front of a computer. I think there's some advantages there.
Yeah. Well, that's how most astronomy is done now, right? They're not sitting in front of the telescope. They're in the control room, perhaps hundreds of meters or even hundreds of thousands of kilometers away.
Sometimes they're done remotely. Sometimes you're right there, but you're sitting in front of a screen.
Or they're in Baltimore at the Hubble Control Center. And they're taking their observations. Yeah, astronomy's changed a lot since poor Milton Humason had to sit there and take Hubble's observations for him.
It's now all completely digital, so everything is digital data. All of the stuff we gather in astronomy is all digital data now.
Yeah, they used to be photographic plates, and some poor sod had to sit there.
Ironically,
in typical fashion, let the women do it, and then.
Ironically, nowadays, sitting in the cold outside is mostly confined to the realm of amateur astronomers for the most part. Yeah.
Well, you live in Florida. There's no cold to sit in.
For the most part.
The amateur astronomers are still hardcore. They still do it old school.
Yeah, there's my telescope tripod right there.
Yeah, I have a lot of respect for those people because it's funny because it's one of those fields in which you can find somebody who's an amateur who knows far more than you do. And some of these folks are just amazing in terms of what they know and what they can do, as a hobby. And hanging out with some of these folks, it makes me feel ashamed. It's like, man, I am so lazy. I get paid to do this stuff. They're doing more than me.
Yeah, even though amateur astronomy, as you well know, Brian, has evolved a lot in recent years. Now there's a lot of virtual observations that has been done even by amateurs, and they can remotely view telescopes that are located in other parts of the world.
Right.
So
right.
that's because of technology, right?
Yeah.
So,
This may be slightly off subject, but you did mention about the women not getting the credit for the things they've done in science in the past.
Mhm.
And it brought up something in my head that reminded me. It's true that, just let the women do it was a joke, but actually the first classifications of stars was done by a team of women, I believe. And
Yeah,
then,
it actually it was. I did it in a joking way, but I didn't mean it as a joke. There was actually a group at the Harvard Observatory that had the wonderful name of Pickering's Harem.
right.
They
That's
did
what
most of the heavy lifting. So all of the stellar classification, finding Cepheid variables, was
and
done
then
by
Annie
that
Jump
group.
Cannon came along and squeezed it down, right?
Exactly. So these were amazing women that worked incredibly hard, and only now are we kind of recognizing their efforts.
I guess Henrietta Leavitt was the one who discovered the Cepheid relationship.
Right.
Yeah,
Henrietta Leavitt.
that Hubble used to get enormous credit for his work.
Right. Well, and to Hubble's credit, he was actually an advocate for, everyone to get credit.
Mm-hmm.
He definitely wanted women to get credit for doing the work that they did. But he got the notoriety for it.
Right. Well,
it was more the system than the individual that was faulty at the time. It was the entire environment that was, kind of treating women differently.
Yeah, there was a deeply cultural aspect.
Right, that's what I meant.
Yeah, I mean, the discovery of the structure of DNA depended critically on the work of a woman who didn't get much credit for it.
Yeah. There's a long list of stories we can do where we men need to atone.
Yeah. Well,
Maybe we need another podcast for that one.
Well, we'll have to have a woman. We need to have more women scientists on the podcast and talk about their work. I'm all for that. So I'd like to ask Brian kind of where we are in the state of our knowledge, both controversial and uncontroversial, on the large-scale structure of the universe. I keep reading about things like dark flow and clusters of gamma ray bursts and clusters of quasars and structures that are larger than 1 billion light years. And is the universe really at the large scale isotropic and homogeneous, or is it, or is that just, or is there some holes in that idea?
I don't know that there are holes in it. There are some interesting hints. I don't know what they hint towards, but there are some interesting hints. I think part of the issue is we are reaching a point where we are getting so much data and we're getting so much computational power that, if you look for a pattern hard enough, you will find one. And so we start to find these hints, and these hints could be noise. It could just be noise in the static. We don't know yet. I think by and large, everything, yes, does point to the idea of it being homogeneous, and I think the cosmology principle still holds. But there are some interesting things that show up, cold spots in the CMB, clusters of gamma ray bursts, things like dark flow, and every now and then you hear these research topics. From what I know so far, all of the ones that have come out have not been strongly statistically significant. So they come into the ideas of being somewhat unusual, but not inclusive. And I think it may down the line raise some interesting questions, because there may come a point where we're limited in what we can do. There's a limit to how far we can see galaxies.
Right.
And if that's the case, we may not be able to gather enough data to truly answer that question. There may be always a little bit of maybe in the background. I don't think we're there yet, but it's a possibility. In some of these areas of research, we may find that the evidence is enough to raise a question but not answer it. And we haven't come to terms with that yet.
Well, good. I mean, that's kind of what I was expecting, that we just don't know yet. But and maybe some researchers have been fooled by random data that clusters in places, just like kind of like cancer clusters on Earth. You know, you get,
right.
You get clusters of things. You expect clusters, but
right. If they're truly random, you're going to find some things that look like they're non-random.
Right.
And yeah, you get things like an odd of 1 in 1,000 or 1 in 100, and you go, well, that's unusual, but it's not 1 in 50 billion.
Right now, but is the flow toward the notion that our galaxy is moving towards some kind of great attractor? That's pretty much decided to be real, isn't it?
Oh, it's absolutely real. Yeah. Yeah, we know where the great attractor is. Unfortunately, the great attractor is kind of, in the absolute worst direction that we would have based on where we are. So there's within our galaxy, there's something called the zone of avoidance, which is right in the middle of our galaxy, and it's basically this, observational cesspool. And so everybody wants to avoid it, but the great attractor is in that direction. And as we've moved towards, radio and infrared at high resolution, we've actually been able to go through some of those. And I think also gamma rays, because the low end of the spectrum and the high end of the spectrum tends to be absorbed significantly less by the gas and dust that's in the center of our galaxy.
Mm-hmm. Now,
sounds like we have a ghetto in the galaxy.
Well, we've got
a lot of dust in the center. That's true.
So the great attractor, that's the only implication there is that there's some kind of local, clustering of galaxies. It's not a cosmological issue. Is that correct?
Right. It's not a cosmological issue. Basically, you can say that, even though galaxies are kind of uniform throughout the universe, they clump. So you've got two things. Because of dark matter, galaxies tend to clump more strongly than they would otherwise. And because of dark energy, those clumps tend to spread apart more. So you get more clumpiness with both of those effects than you would just by gravity. And so what that means is, our galaxy is part of a local group that is clustering together. So the Andromeda galaxy and us are going towards each other. We're going to collide with the Andromeda galaxy at some point. That local group is also part of a larger supercluster. And that supercluster is also gravitating towards a very large cluster of galaxies that we call the Great Attractor. And so there's this, large supercluster area. We're kind of on the periphery, and we're just happening to clump towards that area.
Right. So I guess the message then is stay tuned. There's astronomers are looking at all kinds of things. I read a recent paper about a big possible void about 250 megaparsecs in size from the WISE data and from other infrared data. But not everybody's sure that's a real void or just a normal fluctuation. Is that
right? Well, you can find the voids. There is a void that we know. We don't know what the scale of it is, I think.
Right.
So
Okay.
If I remember, there was one void that's related to the cold spot in
Yes.
the
Yes.
black background.
That's the Eridanus super void. I believe it's also referred to that.
Right.
Well, is super void perhaps a bit of hype, or is that?
Super void is kind of a name that's used, so it sounds a little hypey. I think, the interesting question is that you see this void, and it's in the direction of the cold spot, and there was some speculation that it might be enough to account for all of that particular cold spot. And the cold spot isn't that old. I mean, it's because it's cold relative to things that are very hot. So it's like you see a spike. It's not like it's extraordinarily cold in the background. But we know that the cosmic microwave background, the fluctuations can appear warmer when there's stuff in front of it. Because basically what happens is that background light gets gravitationally lensed, and so it gets focused a bit. And so, because just like a regular lens can make something look closer or make something look bigger, it does the similar type of thing with the cosmic microwave background. And so it looks closer and therefore brighter and therefore hotter.
Yeah, I think we should explain. We've known for about 100 years that gravity can focus light, right? So,
right.
That was one of Einstein's earliest predictions, actually.
Yep.
So, let me ask you about that. I mean, we're about 100 years from the publication of general relativity, and there doesn't seem to be any cracks appearing in general relativity, in spite of the fact that at the time Einstein wrote it, there was a paucity of observational data to back it up. We now seem to think it's pretty solid. Is that? Am I right about that? Or
yeah, we actually know it's very solid. We've not only done all of the tests that were kind of the primary tests of general relativity, but now that we've gotten into computational physics and computational astrophysics, we can run computer models and compare them with observational events, and they agree strongly there as well.
Does it? I mean, I guess just as an amateur, it strikes me as remarkable that something that was developed largely out of beautiful ideas and beautiful mathematics turns out to be observationally correct. And it's somewhat to Darwin's ideas, which were, he had no idea how inheritance worked at the time,
right?
But it just seems to get stronger and stronger as time goes on.
Yeah, I think in some sense those really big models are the exception that proves the rule. People look to Einstein's model and they think that's how science is always done, or at least how physics is always done. And that's rarely how science is done.
Right. Yeah, you have to be really lucky in just the right point in history to...
Yeah, and Einstein's kind of a freak in that sense because he published a series of papers in a single year, and all of them are revolutionary. So,
yeah. I think maybe that speaks to the it reiterates. Excuse my stuttering. His genius. In other words, some people saw he wasn't that smart, but you know what? For him to come up with, just like Darwin, for him to come up with these seemingly at the time radical ideas, and for them to be over and over again reestablished by proof of observation long after they're dead, is just shows the genius that some of these people were.
Yeah, but I wonder if it isn't kind of historical as well. I mean, there's other examples in other fields where just a lot of genius seems to come together at one time, and I just, it would seem to be the right time and the right in history we had the right mathematical tools, and we had concepts that weren't working, so it was time for a paradigm shift, and Einstein was the guy who stepped in to that gap at the time it was there.
I think it was probably a combination of the two. You have the right timing, but you also have brilliant people, and sometimes it hits. You get a Darwin, you get an Einstein, and they're not the only intelligent people out there that have done work, but they happen to be at the right time, and they happen to be able to bring the right kind of ideas together to make something that was truly transformative.
Mm-hmm. Yeah, I mean, I when I think, I'm a music fan. I think of that Mozart, Haydn, and Beethoven all knew each other, just and lived in the same town, basically. That doesn't make sense to me, but that historically it was all the setup was right for them, right. and the type of musical education they had in those days, and the type of training they had, and the just where music was at that time. It was a right place for genius to appear, and it did, and in that tiny little area, in that tiny little few decades. And I think you see the same thing in physics, and you see the same thing in lots of other areas.
Yeah, I would say also, I think there's something to the idea that genius breeds genius, in the sense that good ideas feed other good ideas. And so when you put intelligent people together, when there's a lot of opportunity, I think you get a lot of change.
Yeah, well, I mean, like Edinburgh in the 18th century,
yeah,
You had the Scottish Enlightenment, and you had a lot of really, really smart people drinking wine together every night.
Right. Well, I think that says something to, the level of progress that we've made now. The fact that we're in a golden age in astronomy has to do in part with the fact that all of this is being communicated. We now have an internet that allows everyone all over the world to know things almost instantly. If you go to bed at night, you're going to miss something.
Right.
And I think that's part of the reason why a vibrant field now.
Yeah, I mean, I work in the weather satellite area, and these guys are incredibly sophisticated about how they make measurements and of the atmosphere, the Earth's atmosphere. I'm in all of them all the time, and we're at that point now where we have, it's not so publicly known, but our weather predictions are so much better than they used to be. And these guys can tell you where a hurricane's going to make landfall much more accurately than they used to be. That took an enormous amount of work by a lot of people, but a lot of it is extremely sophisticated sensing, and understanding the phenomenology of the atmosphere really well. And, that's kind of gone underneath the radar, but, a lot of really smart people have been involved in that. And, we all benefit from it every day. We no longer look at the weather forecast and say, yeah, right. They know how hot it's going to be tomorrow. Because they do.
Well, I think we're kind of cursed by the idea of our constant successes. We don't notice the successes. What we notice are the failures. That's
true. In astronomy, we have these amazing new instruments coming online now, like ALMA and the Extremely Large Telescope, hopefully not too long, the Square Kilometer Array.
Yeah, LSST.
Yeah. So there's NASA's looking at the next generation telescope beyond Hubble and beyond JWST, and I think that's going to be controversial for a few years before they settle on something. But so where as an astrophysicist, what are you most hoping for? Would it be gravity waves, or would it be ultraviolet? What would it be?
I'm hoping for the unexpected. I think I'm really interested in kind of the exoplanet searches. It's not my field, but it's just that idea. I think partly because I grew up with Sagan, and Sagan never knew of an exoplanet.
Thank you for that.
He never knew of an exoplanet. He thought they were out there, but there was none that was discovered in his lifetime. And now we've got thousands of them, and I think that's an exciting thing. The other thing that I think is really exciting is the idea that astronomy in a big way is moving towards public information, which I think we don't know what the ramifications of that are going to be, but I think they're going to be exciting. If you take something like LSST, which is being built in Chile, they're taking a very different approach. Already, most of the observational data that's out there either goes public immediately or it goes public after a release period. And so anyone on the planet can access a lot of this observational data. As long as you have an internet connection and as long as you have a place to access it, you can do this. LSST is going to cut out the middleman. They are going directly from observational data to a web page. So every day when that data gets gathered, it gets sent right out to the net. And the idea of asking for observational time goes away. At LSST, no one's going to be able to say, I want to have time on the telescope. No, there is no time on the telescope. What you have to ask for is, can someone pay me to look at this data? Because that data is already out there.
Right.
And that's a radical shift. Not every field of science does that, but I think in many ways every field should.
Wow.
It makes it very clear that this is a human endeavor, and all of humanity does astronomy.
Yeah. One thing.
Where we go.
Can you tell us, like, first of all, what does LSST stand for? And
I'm gonna mess this up. I think it's Large Synaptic Survey Telescope.
Okay.
Yeah, that's right.
Yeah.
Yeah.
It's a sky survey telescope, so it is going to view the entire southern sky. I think once every 4 days or something. So it is different in its design in that it's an 8-meter telescope. So effectively, it'll be a 6-meter telescope, but it has a huge field of view. So most telescopes that are large mirror telescopes have a very narrow field of view. So you can look at a small thing here and then go to the next one and look here and then go next one and look there. But you can only look at a small patch of sky all the time. LSST has this radically different mirror design. So it has this huge field of view all at high resolution. So the limiting factor is not the amount of light gathered, but the limiting factor is how much data you're going to have to process. Astronomy at LSST is more like Google than it is like a traditional telescope.
Is this the one that I heard about going to be built or in Australia?
It's going to be built in Chile near Gemini.
Oh, Chile.
I think you're thinking about the square kilometer array. Part of that's going to be
is where it's going to be.
Oh, that's right.
And
I'm sorry.
they're already working on it. They're doing the construction on it. The mirror is already built. I'm not sure exactly what the timeline is, but it's a massive data dump. And here's the entire southern sky. Every 4 days, here's the entire southern sky. And anyone can look at it. And the real challenge is, how do we deal with all that data? So if someone is interested in binary stars, for example, how do they find the binary stars out of all of that data?
Wow.
And how can you ensure that they can find their binary stars while someone else can find quasars, or someone else can find, look at exoplanets and things like that? It's a huge challenge, but it means anyone can do it.
Right. Well, just a few episodes ago, I guess it was, we were talking about the effort to mine the WISE data for Kardashev 3-level civilizations in other galaxies.
Yep.
A very clever effort there, but I mean, they have a tremendous amount of data from WISE just itself, and it took a lot of effort to filter things through to find what they were looking for.
And that's I think the revolutionary change is that as we get more computing power, as we get greater search power, it's going to be easier to do this, and people who are interested in different things are going to have a wealth of data at their fingertips that they didn't have.
Yeah, well, in the case of the WISE data, there were quite a few spurious things that had to be filtered out. So it took some smarts to go through that.
Yeah, it's not going to be easy, and it never is. But
yeah, I mean, just airplanes flying over this telescope I'm sure they'll have an algorithm for dealing with that, but it's the sort of thing they're going to have to do.
Yeah, planes move, and stars don't in the same way.
Planes, comets, asteroids,
shooting stars.
Yeah,
you get meteors, and they're going to be in your field.
So the and this will have the same problem with the square kilometer array. Will generate huge amounts of data, vast amounts, multiple beams, and that kind of. Well, you mentioned the exoplanets. Let me ask you about this week's announcement. There's been a lot of confusion, I think, about what an Earth-like planet really means.
Yeah. I think Ethan Siegel referred to it as a sub-Neptunian. I think he was saying it's probably going to be gassy. There's given its size, and the thing is, we don't know what its mass is. Right. Given its size, it could very well be a very small, almost gassy planet. It may have a rocky surface, but it could have a very thick atmosphere. It could be very different from what we would imagine an Earth-like planet to be. And I think he's got a point. There's other people that would argue that, in fact, it could have a less thick atmosphere depending on what its density is and what its consistency is. But I think what's really interesting about this is its orbit, in that, it's not a Jovian planet. It's not a Jupiter-sized planet. It really is in the general range of being an Earth-sized planet, under 2 Earth radii. So, it's in the ballpark at least. But its orbit is basically smack dab where Earth is for that star. And it's a star that is pretty similar to what the sun is. It's a little bit older, but you're finding that, here's a planet that has an Earth-like orbit around a sun-like star. I don't think that's insignificant. I don't necessarily think that it's going to be a habitable world. I think, there are problems with that idea. But we're finding Earth-mass planets around sun-like stars now.
Yeah. So the Earth 2.0 hype is perhaps a bit premature.
Yeah, I mean, I think you could say it's within the realm of possibility that it could be habitable by terrestrial life, but not a realm of certainty. If it were an Earth's massed planet, I think it would be much better odds. But we're finding water everywhere. We're finding now planets everywhere, and we're finding planets around stars like ours. We know that planets are common. We know that habitable zone planets are common. The question is, how far are we going to go before we find an actual Earth-mass planet around a sun-like star?
Right. Well, we have tests coming up, and we have possibly a European satellite as well that will search sunlight.
Yeah, we have Gaia, and you're going to have data from that, and you're going to have data from LSST, and you're going to have, all of these a lot of these telescopes that have other missions have to do the type of thing that's necessary to look for exoplanets. So Gaia, for example, is looking at the spectrum of stars in order to find their Doppler shifts. It has to find out what the positions are, as well as their parallax distances. Well, that's data that can be used to find exoplanets, because if you know the spectra, if you know the light intensity over long periods, well, you can use that to find planets.
Right. Yeah, that's how most of the early planets were discovered, with the spectra slightly shifting.
I think in the next couple of decades, it's going to completely transform what we view as exoplanets, because we're going to just have so many of them.
Yeah, that's what I was going to say. One of the significant things is that other than the discovery of this particular planet, is the fact, I believe, that their catalog has gone up by 500 planets. So, right, I think, Brian. So it's now.
I think that's in the general range.
46 over 600. Over 4,600 planets, just candidate planets from the Kepler catalog alone, if I'm not mistaken.
Right.
That's a large number of exoplanets if we think about the time, right, when these all have been discovered.
Right. Well, I think you can go back several decades, for example, and say something like quasars. Like, we found a quasar. Oh, we found another quasar. Oh, this is news. We found another quasar. And now it's like, how many quasars? I don't know. Look at the database. I couldn't tell you. And we're going to find in 10 years or 15 years, it's going to be like that with exoplanets. How many exoplanets are there? Oh, yeah, I don't know. Go to the database. What's it say on the official site? I don't know.
I was wondering if it would be all right, since this was the subject I wanted to ask about in the thread. And since you're actually talking about it, I was wondering if it was right, Paul, if I go ahead and ask my question.
Well, yeah, go ahead.
Brian, there was 3 questions I had in mind. Well, one was just brought up, and that is the star that the recent one that was just discovered. The star is said to be almost exactly, but almost is the key word. Do we know the exact, like our sun is a G2? Is this star a G2 or is it a G1?
The star is a G2. I think it's less than 10% difference between the mass of our sun and that.
Okay.
So in astronomical terms, they're the same type of star.
Okay. So the second question, slightly off. Speaking about planet hunting, they got this new technique that they're still trying to make or to make better. This star blocker thing, in order to see atmospheres.
Yeah.
Do you know if that's going to be being used very soon, or is it something? I mean, I understand that they could put one inside of a telescope, but there's that one project that they're talking about sending out this big fin thing, which they're working on actually.
Right. I don't know very soon. I would suspect that it's going to be the next thing that is kind of the big exoplanet research. We know that we know there are exoplanets out there, and so the next question is going to be, can we actually observe these atmospheres? Right. It's the only way we're going to find out whether something is actually habitable or not. Even if we found an exactly Earth mass planet and exactly going around a G2 star, if this newly discovered planet were an Earth mass planet, we still would know nothing about whether it's habitable or not.
Right. Right.
All we know is
the hype always tells you, like, oh, another Earth 2, oh, let's go there right away. That's stupid.
We don't know if it has water. We don't know if it's got a reasonable atmosphere. We don't know if it has a magnetic field. We don't know any of those things.
Right. Right.
And if we could look at the atmospheres of those planets, we could find out all of those things. We would know whether or not it has water. We would know whether or not it has a magnetic field. We would know if it's producing organics that would be indicative of life. Those are the types of things that we want to have. I think once we've gone through this period where we find exoplanets everywhere and Earth-massed exoplanets everywhere, I think,
which leads to my third question.
That's the next mission. Can we find planetary atmospheres? Can we observe them? And I think that Sun Shield has a good chance of doing very well.
Which leads me to my third question. It seems like they're talking about G-class stars, and then they talk about M-class stars. Why aren't they even thinking about K-class stars? In my mind, K-class stars are probably the most important. In my mind.
I think because they're kind of like the toe-headed stepkid, in the sense that red dwarf stars, M-class stars it's easy to find planets around them because they have a small mass, because they have a small radius. Any planet of measurable size makes a bigger dip relative. It blocks off a larger percentage of the star. So
that much I know, but in other words, they have talked about the G class. They just found one in the data from Kepler.
Right.
And they talked about that fact that being the M class stars are so tiny, you can see the bigger dips and all that. Mm-hmm. But they seem to be avoiding the K-class stars. Is there a reason for that, or is it just coincidence?
I think it's just coincidence in the sense that M-class stars are far more common than K-class stars. And K-class stars are more common than G-class stars. But I think just in terms of the media, they're far more common, so we find more of them. If you look at kind of the candidate planets, most of them are red dwarf stars, and that's just because they're more common, they're easier to find. We've got a bias towards that observationally.
Just by statistics alone, right?
Just by statistics alone. And so you can look, I think there are a couple of K-class stars that have possibly habitable planets around them.
Wasn't Kepler 186 a K? I'm not sure.
Yeah, I think it may be or close to it. But it doesn't have the same thing where you can say it's a G2 star. It's a sun-like star.
If it's not the sun, it's not us.
Yeah, and I think a part of that is just in terms of our own biases. Within the media, we want to find an Earth mass star around a sun massed star at the same orbit that we have, and barring any other evidence, we'll say we've got it. And that's just because we found then a planet like ours. A planet like ours is not the only one out there. But we have lots of other things that we know that point to life possibilities being on planets we don't expect. So warm Jupiters, for example, could have moons that are rich in water, that would be perfectly habitable. And in many ways, they have a better opportunity than we do.
Yeah.
You have red dwarf stars that have far more common in terms of being in a habitable zone. They could have life forms, that we don't have to have, even if we just limit ourselves to water-based, carbon-based life that's similar to ours.
Right.
Even that, we're still not limited to rocky planets like ours. It could be.
It just seems. It intrigues me, and it is my idea that I have this strange feeling, call it a premonition. Of course, I don't really believe that stuff, but it just seems to me that there's like a pattern throughout science discovery that the thing that we weren't talking about much is the thing that we actually find. Now,
yeah, and I think
K-class stars, like you said, are more common than G. And not only that, they live longer, giving more time for any life to form and turn into intelligent life if it should happen. So there's a
Right,
better
and they're less
chance, at
subject
least.
to things like solar flares.
And then you don't have that tidal locking problem that they talk about for M-class stars. And
Right.
it just seems to me the K-class star is the way it'll go. It's like, let's look for some more Ks.
Well, and that, I think as we get better observing tools, I think you're going to find more of them. I think part of it really is just having to do with the bias of what we have.
Right. Yeah. But they're common stars, and we'll see a lot of them in the database.
Yeah.
Now the tidally locked stars is still controversial whether they may. I'm sorry, tidally locked planets. It's still controversial whether the climate there would be habitable or not.
Right. Yeah. Also, red dwarf stars are controversial because they tend to be. They can give off large solar flares or coronal mass ejections that can be harmful to life.
Isn't that mostly when the younger M-class stars?
It is when they're younger. So one of the ideas is that even though they're more common, they may basically fry any possible life there, and then basically make anything close enough to be warm dry. So it's not like it's going to cause a catastrophe and the civilization is going to be destroyed. But early on, you have a close planet, you have a lot of solar activity, and then the most of the volatiles will just boil off. So what you're left with is a husk.
This is why I have such an affinity for the K stars.
Yeah, I mean, in many ways, the ideas of life on exoplanets is kind of like cosmology 30 years ago. Everybody's got an idea, and you can't prove me wrong.
Well, I mean, I find it intriguing that it was, like you said, 30 years ago, they were arguing whether or not it was even possible for to be a stable orbiting planet around a binary or multiple star system.
Right.
And they found at least 2 Tatooines,
Yeah. We know that now, and with computer simulations, we know that now.
Great. Okay. We as we get a bit over an hour, I just wonder if anybody's got any last burning questions for Brian.
I'd like to ask about, you said at the beginning that the theories, like the static state theory of the universe, bit the dust long ago. How secure do you think the current lambda cold dark matter theory is? Can you see perhaps 20, 30, who knows how many years in the future, someone coming up with a better theory, or do you think it's going to stay with us? Will we find dark matter?
I'm willing to suspect that we'll find dark matter. I think there's a great deal of evidence to support the idea of dark matter. And one of the things that's not talked about a whole lot is all of the theoretical attempts to kind of eliminate dark matter are constrained by general relativity, are constrained by Newtonian mechanics. And so there are certain constraints that general relativity and Newton already places on any theory of gravity. And it basically eliminates the kind of thing that you would need to really make an effective modified gravity model that matches what we're seeing. And so, I think that combined with a lot of the evidence in terms of galaxy collisions and gravitational lensing, we're not sure what it is, but there is something there. In terms of the overall model, I think it will work as well 100 years from now as it works now. And I think in the same way that Newton is technically wrong, but still incredibly right, I think the model that we have now is, even if it's technically wrong, is still going to be incredibly right. It's still going to be a good approximation to what the universe is like, even if it's not the exact answer. And I think that because we have tons of data now. I mean, the thing is, we have lots of observational data, and it all converges on the same type of model. So we're not reliant on just galaxy rotation curves. You can look at the cosmic microwave background, and we see the fluctuations in it at the scale that dark matter would say, and it's at the same level that we see in gravitational lensing. It's the same level that we see in large-scale galaxy clusters. All of these things, they overlap in terms of the amount of dark matter and dark energy that they predict.
So if you were to guess at what dark energy is, what would you say?
I kind of have a bias in the sense that, my training is in general relativity, and a cosmological constant is perfectly valid within the model. So far, it matches a cosmological constant. So it may just be that dark energy is what space-time does. It's just a property of space-time, and it's what we call the cosmological constant.
So we'll never find anything like a dark energy boson or anything like that.
Well, that's a separate thing, because if you're talking about a boson, you're talking about a quantum theory of gravity.
Yeah.
So maybe there would be. I don't know, but I don't think. I don't think it's going to be a force like quintessence.
Quintessence. That's what I was going to say.
It's force.
That's the energy from Megatron.
Right.
Cybertron.
From Cybertron. Yeah. So I'm partial to, the cosmological constant. But to be honest, when I was an undergrad, I was partial to modified gravity for dark matter, and I was wrong.
Were you surprised when dark energy first appeared? Was it a big shock to you?
I think it was a big shock that they could actually observe it, that they could actually confirm it.
Yeah.
It was one of those things where, because it's so close to zero, it's so small. And so it was one of those things where you can look at these models, but if you assume them of any scale, they don't match what we see. And so I was kind of surprised that you could see it. It was just on the edge of being able to be seen, but not enough that it would be, easily seen 20, 30, 50 years ago.
I think a lot of surveys at the moment are designed to give us a better understanding of what dark energy is. By,
Right.
Producing better measurements, standard candles.
Right. Is it uniform in all directions, so on and so forth, yeah.
Yeah, so hopefully, 20, 30 years from now, we will have a much better understanding. Do you think it's going to take someone like perhaps another Einstein to take us to a better understanding, or do you think it'll just be a very small, gradual step?
I think it will be somewhat, if I'm just speculating, I would suspect that it will be something like the quantum revolution.
Right.
In the sense that it will be a lot of bright people, several dozen bright people who come together in a very quick span of time to revolutionize our understanding of the universe.
And perhaps quantum gravity.
And craft quantum gravity. Yeah, I'm hoping, So I think, start funding African schools, because we need those kids in the game. We need every hands on deck.
Well, with 7 billion people, we ought to have at least a few that are ridiculously intelligent, right?
Yeah, well, see, that's the amazing thing, is that with the observational data being out there and with the computational data being accessible, everyone on the planet can come in.
Astronomy has led the way in making data accessible to the public, citizen science projects. Does that make you proud? Are you proud of your field for doing that?
I'm very proud of my field, in the sense that there's a lot that I like about it, and the openness of it, the collaboration of it is something that I'm proud of. I can't take credit for it, but I like that. I think those aspects aspire to the ideals of what science should be.
Yeah, they do. Why don't geologists, biologists, geographers, follow your example? That's what I'm waiting for. The rest of the science community to go open access. What's their problem?
Yeah, I think in some ways they don't have to. And astronomy has always had to. It's like visiting Chile was a kind of a great experience in that sense, in that Chile has incredibly wonderful skies. It does. Its geography gives it that gift of incredible skies. So even back in the 60s, if you want to have access to that kind of sky, you have to work in Chile. So astronomers now have to collaborate across multiple countries to do this. And, we don't have the luxury of saying, well, here, I'm in Rochester, so I'm going to build a big telescope in Rochester. It's worthless because we have tons of clouds and rain, and it's just not good for optical astronomy. And so there's nothing I can do about that. Even if I, was wealthy as Bill Gates, I couldn't build a telescope in Rochester because it doesn't do any good. I'd have to go to Hawaii, I'd have to go to Chile, I'd have to go to other places where it's dry and high. And so we're forced to work together and we're forced to collaborate. And astronomers are also used to working on a budget. They've never been traditionally a large, expensive field. They're not the Manhattan Project. They're, well, please just give me a telescope and then leave me alone and I'll be fine.
I think Tycho Brahe was probably the peak of the budget for astronomy.
Yeah, Tycho Brahe was kind of the peak of the budget. And so you see that tradition. We've got a long tradition of that. And you see that in something like ALMA, which is really kind of amazing to see because it is not spearheaded by one country. The analogy that's given with ALMA is it's like the UN. You have multiple countries working together, and no one's in charge. They all have to work together. They all have to collaborate. They're all pitching in money to do this research. And so there's Europe and the United States and Japan and Chile are all coming together as an international collaboration. And what's interesting is not only do you see that in terms of the astronomy, but you also see this in terms of the political ramifications. So when we were in Chile, one of the things we did is we went to the State Department, we went to the U.S. Embassy in Chile. And they're deeply interested in this because it is a way of strengthening international relations that is both peaceful and relatively inexpensive. You're not giving Chile weapons. What you're doing is you're building telescopes there. And all of a sudden, you now have a stronger alliance, which is good for the United States, it's good for Europe, and it's good for South America, and it's good for Chile.
Yeah. Okay. Any other burning questions for Brian?
I was going to ask him to sing us this song.
Are you serious?
No. No.
Okay, you do not have to be able to sing to be on the Unseen podcast.
Oh, that's a good thing. Yeah.
Well,
but if you can't sing well, please don't.
I guess,
I did enjoy it though, Brian.
Yeah.
Well, I'm glad that you did. Yeah.
Okay. Well, I think this is a good time to wrap it up. I'll go around the virtual table one more time, let everybody have a last say. We'll start with you, Adam.
It's been an absolute pleasure. I've very much enjoyed meeting Brian. Ciro, Patrick, been an honor. I'll see you guys again sometime.
Yes.
Paul,
Yeah.
nice to see you as ever.
How about you, Ciro?
Yes, obviously, as I said, it was a good opportunity to be able to see Brian face to face, virtually say face to face for
Virtually
the first
face to face.
time. Although we've been exchanging things on some of the threads, and so we have our own little conversations every now and then. But otherwise, also thank you, Paul, of course, for the opportunity to be a part of the panel tonight.
Oh yeah, well, Ciro, you haven't been on in a few episodes, so it's good to have you back.
Thank you.
Patrick.
Yeah, again, this is actually better than I expected. Brian, it's a huge pleasure to meet you and talk. Just to listen to you, even if I didn't get a chance to ask questions, which I did. And thank you, Paul, for squeezing me in here to meet Brian. So I don't know what I could say. This is one of my favorite podcasts from you ever.
Okay, well, yeah, I think this is probably one of our top 3 or 4 episodes so far. And I'd like to thank Brian Koberlein very much. Brian, we we can catch you on One Universe at a Time. You're both your podcast and your blog.
Yep.
And you put you seem to, during the academic year, it seems like you're putting out about once a week with the podcast.
Yeah, we're still trying for once a week. The problem is that everybody's bailed over the summer, so trying to get people in.
Yeah, well, it's a podcast I recommend. You can hear a leading thinker on one topic, and then Brian gets queried on another topic. So,
Right.
And it's very focused and to the point. So, well worth listening to. And unlike us, who we ramble all over the place, but the Brian hopefully will continue posting about all kinds of astronomy and astrophysics topics on his blog, and also you put your posts on Google Plus as well. You can be followed on Twitter I think it's at Brian Koberlein. Right?
At Brian Koberlein. Yeah.
Yes.
I have an unusual name, so if you just look up Brian Koberlein, you're going to find me.
Right. And we'll have all those links in the show notes at unseenpodcast.com. Now, folks, if this is an open participation podcast, if you'd like to join the panel, send me an email at unseenpodcast@gmail.com, and I'll tell you how you can join. So far, we've had 15 panelists in 16 episodes, so we're hoping to actually have more panelists in episodes at some point. And these guys, Patrick, Chiro, and Adam, had all been on before, but hopefully somebody new soon. And we will see you next week at episode 17. The topic is not picked, but I think SETI is definitely going to be near the top of the list. And I'd like to, once again, thank Brian, thank Chiro, Patrick, and Adam. And this is the Unseen Podcast, episode 16. It's the 24th of July, 2015. Check us out at unseenpodcast.com. And good night.